Alright, so in the last video we saw how to use Lagrange multipliers to solve an optimization problem involving functions of several variables. And in this video what I'm going to talk about is the application of Lagrange multipliers. So just to remember the equation that we used. We have our function being optimized, we have our constraint function called g, and then we have, obviously we take the gradient of those, which is the first partial derivative, and that becomes a vector. And we have this Lagrange multiplier, which is just a unique number that we solve for, essentially using 4 equations if we have 3 variables involved and so forth. In this video what I'm going to talk about is how we can apply this to actually find extrema values on a function, the same way we would using the second derivative test, but this is actually quite a nice method. So I just wanted to give you an example of that so you know that Lagrange multipliers can actually be used for a lot of other things. So let's have the function of t variables equals to 5x minus 3y, very simple indeed. And then let's say we want to find the maximum and minimum values within the constraints that of the circle x squared plus y squared equals to 136. So obviously if we have a function that is a surface in this case, and we're confined to this circle centered at the origin, which has this radius, which is going to be the square root of 136, then obviously what we want with this is we want to find, so if the function in this case it would actually be something like a plane, we want to find the maximum minimum values of that within that circular boundary. So that's what the constraint equation in this case is doing. So we want to find maximum and minimum values of that given that constraint. So we already talked about how with the constraint function what we're going to do is we're going to make a function equal to the constant. So that means that the expression here is going to become the function. Alright, now we have 2 functions, we can start solving for this. So let's set it up. So that's going to be a vector of 2. The first element is going to be a partial derivative of x with respect to f. Second one, partial derivative of y. So this one is going to be what? This one is going to be 5 and minus 3. So that one is very simple. And then for g we're going to have the following. So we have this function here, so that's going to be 2x, and this is going to be 2y. So once again, very simple. So now what we're going to do is we're going to set it up the equation in the following way. So we're going to have this vector 5 minus 3 equals to the Lagrange multiplier times 2x, 2y. And I'm going to apply the same method that I used in the last video, which is basically I'm going to solve for lambda in each of these equations, such that I can write it all in one line. So I'm going to write lambda equals to, for the first line, is 5 on 2x. And then for the second line, I'm going to have minus 3 on 2y. So now that I have that, I can actually start solving for this. So if we grab the equation 5 on 2x equals to minus 3 on 2y, we can cancel out the 2's. And then 5y equals to minus 3x, or we can have y equals to minus 3 on 5 times x. So now what we're going to do with this, since we only have 2 variables, we're going to plug this back into the constraint equation, which is x squared plus y squared equals 136. And this is going to be x squared plus minus 3 on 5 x squared equals to 136. And then once we rearrange those terms, we're going to get the following value. So x is going to be approximate, it's actually going to be equal to plus or minus 10. So it's going to be plus or minus 10 because remember we took a square root, so we wanted to find that. So that means that we're going to have this, and that means that for y values we're going to have the same values, but remember y values are negative times x, so that means that this sign convention is going to be inverted, and that's why we write the minus sign on top of the plus. So if we put 10 in here, that's going to be 6. So what this means is that when x is equal to minus 10, then y is equal to 6. And then when x is equal to plus 10, then y has to be minus 6. And that's why we need to make sure that we're careful with this notation. Because remember, when we're finding maximum and minimum values of a function within a particular constraint, we actually need to know the specific coordinates. We can't just like go around picking whatever numbers or whatever combinations of x and y we want. We need specific points. So in this case, we have one of these points is going to give us a maximum and one of these points is going to give us a minimum. So the way we test that is we plug them back into the function itself, and that's going to give us the answer. So let's plug those values back into our function here. So f of minus 10, 6 is going to be minus 68. And then the function at 10, minus 6 is going to be equal to 68. So right away we can see that this is the minimum and this is the maximum within that constraint of the circle x squared plus y squared equals to 136. So within that boundary we found that. Actually I should have written as less or equal than, because that's usually better because that includes the whole region inside that circle, but you get the idea. We wanted to confine this to that particular region. And so what we did with this was obviously we wanted to have a pair of functions or a pair of values that will give us minimum and maximum, and that's what we did. We have the specific coordinates that give us that value, and we have those 2 points on that particular boundary that will give us those extreme values. And this is just one of the many other applications of Lagrange multipliers to optimization. But I thought it would be a really good idea just to show you how it can be used to find maximum minimum values of functions as well. So I recommend that you do some more research. If you're interested in finding the applications of Lagrange multipliers, they're really common in economics and engineering and science as well. So there are a lot of applications that I won't cover in this series, but this is just to show you a few examples of what they can be used for. And in the next video, we're gonna get started on some coordinate transformations using partial derivatives, and then we're gonna move on to multiple integrals.